Okay, let's try to get through this. This is atomic mass. Atomic mass is based on the relative percent abundances of each isotope that exists for a particular element. This is hydrogen. Hydrogen has three isotopes. They're hydrogen because they all have one proton. Hydrogen is a little odd because we have names of the three isotopes: protium, deuterium, and tritium. This is non-radioactive, this is radioactive, and this is radioactive and it's artificial. Now, the difference between radioactive elements and non-radioactive elements chemically is that the non-radioactive elements and the radioactive elements both react and behave exactly the same. There is no chemical difference. The only difference between radioactive elements and non-radioactive elements for a particular the set of isotopes is this: radioactive isotopes are radioactive. The non-radioactive isotope is not radioactive. Chemically, they're identical. So these three isotopes of hydrogen behave exactly the same. They make water, they make chemicals, they react and behave identical to one another except for the radioactivity. I'm making these numbers up. I'm simply saying that the percent abundance of protium is 98%. It's 98%. This is 1.9% for deuterium and 0.1% for tritium. Yes? Now, if I base this on 100 elements, 100 isotopes for hydrogen, this is 100. That's what I'm basing this on. This is a little calculation down here, ignore this. So 98 plus 1.9 plus 0.1 is 100. Clear? So the total mass of protium, the mass number is 1, 98 atoms are protium, that's 98. 98 times 1 is 98. 1.9 times 2, that's the mass number of deuterium, is 3.8. Tritium, the mass number of 3 times 0.1 is 0.3. The total mass of 102.1, and 102.1 divided by 100 is 1.021. That's not the correct atomic mass, but that's not the point. The point is, given some fictitious data, which is consistent with the real data, in that most prevalent, next most prevalent, and not much, you get a decimal. You don't get, the mass number is a whole number, but the atomic mass, because it's based on percent abundances, you get this decimal value of 1.021. So that's where those decimals come from. And if you look on any element on the periodic table, especially ones that are kind of less than like 209-ish, in terms of mass, you're going to get those equivalents. Because the ones that are in parentheses, it's hard to calculate the isotopes. They're not around very much. And so for a very long period of time, so it's difficult to come up with the atomic mass as we just did for hydrogen. So that's where those decimals come from. It's simply this: you list the isotopes, you list the mass number for each isotope, you list the percent abundance, mass number times percent abundance, if you're assuming 100 atoms, is going to equal a total mass for that isotope, add up all of the masses, divide by 100, and that's your atomic mass. And that's it. Thank you.